guys, so welcome to the third and last part of the deep learning masterclass. So in the previous two parts and sessions, we had started with deep learning. What was it? What is all about the buzz about deep learning? How it evolved and how did deep learning come into practicality in these recent 20 years? Then what are the different tasks associated common tasks that are in deep learning? And then what is deep learning, just a bit of introduction about neural networks, and then we gone through about the neuron. So what's a neuron, so what's a biological neuron, and what's an artificial neuron, so what are the key differences, how does the neuron work, what is an activation function, what are the different types, how does it help in the decision making for a neuron, so how does it activate, or how does it participate or contribute in the decision activity making process. And then after that we had seen the different types of neural networks. So once we covered an individual neuron, we gone through the different types of neural networks. So how a neural network is constructed, what are the different types of neural networks or different type of data. And then we took the artificial neural network and we came through a golden process, or the heart of deep learning. We came through that process known as backpropagation. Backpropagation is the heart of the deep learning algorithms, and it is the way by which the deep learning algorithms train and evolve and get better and adapt to the data. So we saw the 5-step procedure by which we will be able to implement backpropagation, and how these 5 steps are used to update the weights and biases, that is the parameters in the network, and make it better than the previous version. Then after seeing the backpropagation, we had gone through the traditional or the conventional deep learning pipeline. So how a deep learning algorithm is designed, or how do you develop a deep learning project, what's the pipeline there, and what are the components or steps inside that. We had gone through all those things. We had talked about the optimizers that are available, the different loss functions and the different metrics. We didn't go in depth, but we just had covered the basics, like what does an optimizer do, what's a loss function do, and what are the different types that are available. And after that we had came into the different challenges that we observed while implementing deep learning. So in that we came specifically in two topics: model training, the underfitting versus overfitting. I gave some great examples on the education, like how we prepare for exams, that correlation or that analogy, how we can map it to underfitting and overfitting to remember them. I hope you like them. And we then went into another problem called vanishing gradients and exploding gradients. How do they occur and why does it occur? So, having said a small recap of what we have covered in the past two videos, this video, or the last video of the deep learning masterclass, is going to cover two topics. The first topic is the convolutional neural network, and the second topic is the solutions to the challenges. In the previous video, we saw the challenges, and in this video, we're going to see what are some potential solutions we can give to overcome or mitigate those challenges and issues we find in deep learning. So the first part is going to be the convolutional neural network, and that is where we are going to start this session today. So before going into the convolutional neural network, I would like to just save a few basics of image, because the convolutional neural network has been primarily designed for image data. It's not necessary that should be used only for image. You can use it for any type of data. You can use it on text, you can use it on time series also. It's your wish. There is no compulsion or there is no pressure that you should use this for that only. There's nothing sort of things in AI. You can go bizarre, you can go any combinations or any trial and error methods you want. The more bizarre you go, the better and innovative ideas you come up with. So it is primarily designed, or the way CNN started were for images. So before going to CNN, I would just like to talk about a few basics of image. So what is an image? How does the computer understands image? So this comes in the side of image processing and computer vision, which I'll be dealing in depth later. But just as of now, understand what the image is. So an image is nothing but like we see an image is actually a photographic recording of an object. For example, if I have this standard water bottle, so if I take a photo of it, that becomes the image of this particular object. So the object is present in an image, and this is how we see. So we see this image with the help of colors. Our eyes work in a different way, so our biological visual system tries to understand the image with its properties, with the shape, size, colors, and all the other things. But computers can't understand those things. Computers read images in form of numbers only. So in terms of computer science, we can say image is an array, or it's a collection of some elements. and that elements are referred to as pixels. So pixel is the unit quantity of an image, and voxel is a unit quantity of a volume. So volume is a combination of images, right? So if you take one piece from the entire volume, it becomes a voxel. So image is basically, they say image is a two-dimensional, but actually in reality image is a three-dimensional object, and volume is a four-dimensional object. I know this defies all the things that you have learned till now. I'll explain what are the three dimensions. So an image basically has three dimensions. The first is the height, the second is the width. So height cross width is the rectangle or the square that you construct, and the pixels are present. So a tiny cube plus tiny square inside that whole picture is a pixel, and you will have that much amount of pixels. And the third channel or the third dimension is what we call as channel. So is it a black and white image or is it a color image? So if it is a black and white image, you will have just one channel, that's a grayscale. But if you have a color image, then you'll have three channels: red, green and blue. You know the basics, right? RGB are the primary colors. From these primary colors we can combine and create as many colors as want, that are called the secondary and derived colors. So these three primary colors constitute the third channel, and with the help of RGB you can create color images. The images that you see here are created with RGB only. So this image, for example, I've shown in the slide here is just a photo with a letter A, for example. So I've considering this as a color image. You can see the height is 30 and the width is, sorry, the width is sorry, yeah, the height is 30 and the width is 30. So 30 cross 30 is the image, but the computer will then understand it as a array of 900 elements. So that's why I've mentioned 900. So it will have a two-dimension array basically. So in one dimension you'll have the rows, and in the second dimension you'll have the columns. So it's constructed in that way, and the three, so we'll have three A's like that. So one, so if this individual image A that I've represented, in the back we'll have three A's. So one will be in the red channel, one will be in the green channel, one will be in the blue channel. When you combine these three together, you get this color image. So this is just the fundamentals. Let's not go deep into the images. That's not the agenda, or that's not the plan of this video. This video is just to understand about deep learning and convolutional neural networks. So now coming to the main star of the show, convolutional neural network. So the CNN is a neural network that is evolved from the ANNs, and it has been designed primarily for images. As I said, it's not fixed for images only. You can do it to any type of data types. It's your wish. The one of the important properties or interesting properties in convolutional neural network is partial connectivity. So I think long back. Yeah, you can see in this image, in the first one is a free forward neural network or an artificial neural network. All layers are connected. So the neurons in each layer are connected to all neurons in the another layer. You can see the connections moving, right? But in CNN, you don't see that pattern. So it is partial connectivity. So this partial connectivity reduces some parameters, and it reduces the model complexity, and it can help in preventing overfitting or the other things. Okay, we have not gone to the solution part yet, but I'm just saying as of now, we'll discuss this in depth later when we come to that part. But just understand that CNN has some partial connectivity, and it is not fully connected as you see in an ANN. Yeah, so a CNN can be constructed, a basic CNN. I'm just referring basic because there are a lot of different types of CNNs and many advancements have come in that. But a basic CNN can be constructed using these four layers. So you have the convolution layer, you have the pooling layer, you have the flattened, and you have the dense. So it is quite obvious. Convolutional neural layer, so it performs convolution. So people who have studied signal processing, who are doing their bachelor's in biomedical engineering or electrical engineering might know what convolution is. But for the other people, don't worry, I am there to solve this, sort it out for you. So just understand that these four layers are minimal essential layers that you need to construct a neural network, and this neural network works on image data, and it has partial connections. That's all you need to know about the basics of CNN. Moving forward, now we'll come to the heart of the CNN, that is the convolution operation. So the convolution is nothing but the combination of two mathematical operations, multiplication and addition. So you combine multiplication and addition, and that becomes convolution. So you take two different data, you multiply them and add them together, and you get an output that is called the convolution. So for convolution to happen, you need two data. One is quite obvious, since you're working on images, the first data is going to be the image only. But what is the second parameter I should consider? That second parameter, the second quantity that we consider is known as a filter or a kernel. So we define the kernel, we define the dimension of the kernel, and we assign the kernel, and this kernel will convolve with the input image and it will try to produce an output. So why are we doing this? You can ask me. So you can just look at the image. Okay, first I'll explain the operation of convolution and then we'll go to the question of why. So you can see, I'll just give a brief explanation. Don't worry, there are some slides coming up which will give in-depth explanation of convolution. But as of now, I'll just give a brief explanation. So you can see in this image on the right hand side of the slide, I've given a 7 cross 7 image. So there are 49 numbers. I've just numbered. So these numbers, yeah, I forgot to mention that thing. So these numbers are nothing but the intensity of the pixel. So they divide, see, colors are infinite. There are infinite amount of colors. So these we call colors are continuous, but to discretize them or to convert them into discrete variables, they have divided them into 256 shades of gray. So we have the shades from 0 to 255. So the intensities of the numbers or the intensity numbers will vary from 0 to 255, and the number indicates the intensity or the shade of the gray. Or if you take an RGB, then the shade of the red, the shade of the green and blue respectively. So these are what these numbers are referring to. So we have this 49. For example, I've just for the some to understand, I've just named it as numbered it as 1 to 49. In real time, you'll get different values depending upon the image. So we have this image of a 7 cross 7, and we are taking one kernel or filter of our own. That size we have chosen as 3 cross 3, and this is the kernel I've taken, zeros on all the borders, and the center element is 1. Now I am doing the convolution operation and I am getting an output of 5 cross 5. So what do you observe here actually? Before, what I'm doing is, see, this kernel is there, the 3 cross 3 will roll upon the image and it will do the convolution operation, and the resultant of the operation is given on the right hand side in bold values. I have not still mentioned what the operation is, how it performs, but what kind of pattern do you observe here? So you see an input that has a 7 cross 7, and when I convolve it with a 3 cross 3 kernel, I get an output which is 5 cross 5. So the dimension has reduced. This is what we do, or what we call as feature extraction by dimensionality reduction. So the aim of the convolutional neural network or the convolution operation is to extract features from the images by reducing the dimensions. This is the very important point you need to understand. And there are two layers, convolution and pooling, which we'll come with the pooling later. But understand that these two layers, the primary task assigned to these layers is to extract features by reducing the dimension. You take a big image, you apply convolution, you apply these filters or kernels, you construct the dimension, and then it will try to convolve with the image, and it will try to reduce the dimension. And as the dimensions reduce and reduce, rich and rich features are getting extracted. So once the features are extracted, then you go for the classification process. That is same as a 1D classification problem that you've seen in machine learning or ANN can solve. So I hope you have understood. Once again, I'll revise this concept, but now let's focus on how convolution occurs. So you can see here, I have mentioned in the left hand side, just look at the image on the left hand side, you have the numbers from 1 to 49, and the kernel or the filter I'm considering has this value, zeros on the borders and 1 in the center. So now when you apply the convolution, what is happening is, I have mentioned on the right side, you can see in the first image. So you have see the individual elements. So the 0 kernel sits on top of 1 2 3 8 9 10 15 16 17. So you have 1 into 0 plus 2 into 0 plus 3 into 0 plus 8 into 0 plus 9 into 1 plus 10 into 0 plus 15 into 0 plus 16 into 0 plus 17 into 0. So you multiply element wise multiplication, so they call it as piecewise multiplication, and then you add them all together. So that result is the convolution operation. I hope you understood. I'll say it once again. So we have the image, that is the 7 cross 7 image, and we are trying to convolve it with the 3 cross 3 filter. So This filter has these values of 0, 0, 0, 0, 1, 0, 0, 0, 0. So now what happens, just visualize this. I have not created an animation. I'll for sure try to create an animation which will explain, a video animation which will explain it well. So just assume that this 3 cross 3 kernel sits on top of the image. So 1, 2, 3, 8, 9, 10, 15, 16, 17. So these are the 3 cross 3, and above this 3 cross 3, this 3 cross 3 sits on. And so let's say I have my two hands. So this will get multiplied with this with this with this with this. And yeah, my thumbs are not on the same, that's for sure. And then we add them all together. So we are now taking a 3 cross 3 operation and getting a 1 cross 1 value out of it. And you can see the value is 9. So we repeat this for all the different. So now what it will do? Once we have finished 1, 2, 3, 8, 9, 10, 15, 16, 17. Next, move a bit, shift a bit right. So that is called the sliding window. So you slide to the right. Next you take 2, 3, 4, 9, 10, 11, 16, 17, 18. Do the same operation. You have 2 into 0, plus 3 into 0, plus 4 into 0, plus 9 into 0, plus 10 into 1, plus 11 into 0, plus 16 into 0, plus 17 into 0, plus 18 into 0. So you'll get the value of 10. Repeat the operations for the entire image. So next what will happen, it will go to the next window, 3, 4, 5, 10, 11, 12, 17, 18, 19. So as you just go slide and just you move a bit right, you will be getting the convolution operation, and you reduce 3 cross 3 to 1 cross 1, get values, and finally you come up with the reduced image matrix of dimension 5 cross 5. So now I hope you understand why a 7 cross 7 image, when you convolve with the 3 cross 3 filter, you get a 5 cross 5 output. And what is the reason and why we are doing this? Because we are trying to extract features by reducing the dimension. I hope you understood this. And this is how the sliding occurs. You can see the different colors I've applied. So you can see the bottom one, the CN color I've applied. You can see the proper 3 cross 3 that is being occurred. So this kind of a 3 cross 3 filter is what we are trying to apply on the input data, and it convolves. As it convolves, you go to the first 3 cross 3, convolve, get the output, slide a bit right, and then slide. Why should it slide only once? Can I slide it twice? Can I slide it 3 bits later? Yes, of course you can. That's what we call a stride. I'm not going to go deep into CNNs. I just want you to understand the fundamental working. So we have a parameter, we have two more parameters which I have not covered, but I just mentioned, padding and stride. So stride is the parameter which determines the movement. Should I go immediate, or should I just skip one and go to the next one, or should I skip two and go to the next? If you feel the pixels values are almost same and there is no, see what, the pixel intensity of 9 and the pixel intensity of 10 is not that much different. You're not going to observe a big or a huge difference in the gray shade for 9 and 10. So if you feel, no man, I just get the same numbers every time, it's almost similar, why should I waste time, why should I spend more time and do more computations? I want to go fast because I feel that these images, the pixel intensities are almost similar to each other. If I convolve also, I get the similar intensities. I don't feel very much interesting in this. If you feel so, then increase the stride, go for 2, go for 3. So if you keep a stride of 1, then it will go to the next one. If you keep a stride of 2, it will leave 1 in between and then go. So if you keep a stride of 1, it will take 1, 2, 3, 8, 9, 10, 15, 16, 17 at first. Next it will go to 3, 4, 5, 10, 11, 12, 17, 18, 19. If you keep a stride of 3, then it will skip 2 and it will move on. So it's like that how stride works. And zero padding, or padding, is nothing but, so what we observed here, when a 7 cross 7 image is convolved with a 3 cross 3, you get a 5 cross 5. So there's a reduction in the dimension. But if you feel that I don't want to reduce the dimension, I just want to keep it the same, then you apply a layer of zeros above the image. So you just pad or you bound that image with zeros. So now you increase the dimension from 7 cross 7 to 9 cross 9. And in a 9 cross 9, when you apply a 3 cross 3, you will get a 7 cross 7 once again. But why? It's your wish. See, in certain layers, if you feel, no, I don't want to reduce the dimension, let me keep it and then let me later reduce it. So you can do that. But does the image change? Yes, it does. So one thing which I have not said till now is about the kernel. I have just mentioned that the dimension of the kernel is your choice. But what about the values inside the kernel? You didn't say anything about that, is the question that you guys might have. So this is where the beauty of AI lies in. We are just going to define the dimension. The internal values, AI will take care of it. How? the golden word backpropagation. So it will assume initial values, then it will work on the data, it will try to reduce the dimension, do the classification, and find what is the error rate. Then it will adjust the, so instead of weight and biases, the convolutional layer will have these internal values as the parameters. And the neural network will try to adjust the backpropagation algorithm or the optimizer will try to adjust these internal values of the kernel values or the filter values so that better convolution and better feature extraction occurs and you can get accurate classifications or whatever metrics you want in your tasks. So the dimensions is what we fix, but the internal values or the kernel values is determined by the neural network. So I hope you understood this thing. The convolution operation is the most important operation, and if you understand convolution and pooling, then ANN and CNN is almost the same. So convolution pooling plus ANN is a CNN. So next we come to pooling. Pooling also does the same operation of convolution, but in a rapid manner. It tries to reduce, it's a kind of a greedy algorithm or a greedy technique which tries to reduce the dimensions faster. And you saw in convolution, when I apply 7 cross 7 into 3 cross 3, we get a 5 cross 5. I'm not going to go with the formula. I have already promised in the masterclass I'm not going to go deal with most of the maths. There's actually a formula to determine this, but since we are not dealing with maths, I won't go on that part. So we have a formula to determine the dimension of the output based on the dimension of the input, dimension of the kernel, the stride and the padding factor that we are considering. So you can see a dimension reduction, but it is happening slowly, right? So now in the 5 cross 5, if I apply a 3 cross 3, I will get a 1 cross 1, finally one element. Sorry, I'll get a 3 cross 3, and in the 3 cross 3, if I apply a 3 cross 3, I'll get a 1 cross 1. My bad. So 7 cross 7 images, man, is just this tiny. Who's going to use that image? The image that you see here is 1920 cross 1080. I guess I'm not sure on the screen resolution, but that's what a general laptop resolution is. Correct me if I'm wrong. So if you consider this huge amount of 1920 cross 1080, you apply a 3 cross 3, or let's start with square images because rectangular images will go a bit tedious. I'm not going to go into the math as I promised. So let's take a 1000 cross 1000 image. If I apply a 3 cross 3 kernel, I'll get 998 cross 998. Apply a 3 cross 3 kernel, 996 cross 996. Man, when will I reach to the lesser dimensions? I can't process this time. It takes a lot of time. That's where my friend pooling comes to the rescue. Pooling will try to reduce it by 2 or by 4. It will do greedy reductions. So if I take a 1000 cross 1000 and I apply a 2 cross 2, then it reduces the dimension by a factor of 2. So you will get a 500 cross 500 matrix. So how does that operation occur? So you just take a 2 cross 2, a 4, and then it will slide on the image and it will try to take a single output and it will replace that output with that. So same convolution operation, but this is greedy and this is faster and it reduces the dimension quick. So if you feel that your training or if your neural network is taking a lot of time or the convolution neural network is extracting features slowly, just to boost the process, use the pooling layers. So there are 3 types of pooling initially. There are a lot more that have come. So they are the maximum, the minimum and the average. So this defines the operation, and guys, pooling is not learned. That layer is not updated in the training process because we already defined them. We are defining the operations here. We're defining the maximum, minimum and average. So the window that we take, the key difference between the convolution and pooling is that's trainable, this is not trainable. So pooled convolution, the values inside the filter will be determined by the backpropagation optimizer, but these values are fixed because we are going to just take the average, minimum and maximum. So if I take the maximum, it will try to find the max element and it will replace. So let's go with this example. So in a 7 cross 7, I'm applying a 3 cross 3 kernel for max pooling. So what it will do, it will take the per kernel, take the first, go on the first 9 and find the max. So 17. So it will replace this 9, 3 cross 3 with 1, that is 17, and then 18, and then 19, and then 20. So we'll have this kind of uh, operation happening, and it drastically reduces 7 cross 3 to a 7 cross 7 matrix to a 3 cross 3 matrix directly, because you're just taking the maximum and minimum or the average depending upon your operations or depending upon your need. So this is all about pooling. Convolution and pooling both help in extracting features by reducing the dimensions. Pooling does it a more aggressive way, and convolution takes it in a slow manner. And after that, we go for flatten. So as of now, we have come up with a two-dimensional data, but the dense neurons cannot process the two-dimensional data. So we need to convert the two dimensions to one dimension, and this is done by the flattened layer. So if we take a 224 cross 224 image and we apply some 10 convolutions and 10 pooling layers, I'm not going to go with the math. Let's say we come up with 7 cross 7. So this flatten will convert the 7 cross 7 into a one dimensional array of 49. So a 7 cross 7 matrix will convert to a 49 cross 1 array. So now it has become one dimension, and now we can give it to the dense layers, and this will try to do the classification, back propagation, the activation function, whatever things we saw in the previous video. That's the same. I'm not going to repeat those things. The convolution and the pooling layers are the additional stuff we have, and the flattened layer. And with the help of these, we are able to process the uh, structured data. So CNN works on is an algorithm used for unstructured data. It is not on, you can use it for structured, but the design, or it was designed for unstructured data like images, text, graph, audio. So this is all about the working of a CNN, and this is just a sample architecture. The image is kind of blurry, so you can see we have a first CNN layer, and then we have a max pool layer, and then we have a second CNN, second max pool, third CNN, third max pool, flatten, first dense layer and the second dense layer. So you can see the shape, right? It's reducing. So first we had 32, 32, and this 32 here, my friends, is the number of filters. So the filter is not going to be only one. You will have several filters. Several filters will be working on the image, doing convolutions of its own, and then you take the aggregate or average of them, and that becomes the final output. So you have several filters, several dimensions, a lot of complex things going on. That's why, my friends, we call this as deep learning. And next, you can see as we go to the max pooling, the dimension reduces from 32 to 16. See, it's cut off by 2 almost. And next you can see the CNN, it is changing to 16, and then the second max pool reduces to 8, and then the CNN does it 8, and then it comes to 4. So max pool is cutting down the dimensions by a factor of 2. And then you can see the flattened. So when you multiply 4, 4 and 128, so 16 into 128 is 2848, and that is how the flatten has converted this three dimension into, sorry, two dimension into one dimension. It's technically three because we have the fourth, the dimension, or the third dimension, that we say as the number of filters. You can see initially they have constructed 32 filters, then they came with 64 filters, then they came with 128. As I said in the previous video, these are hyperparameters. You could anything of your choice, but generally researchers or people go with the powers of 2 because it corresponds with the memory device, their computation calculation. So they feel it is optimized value, but it's your choice. You can go with whatever you want. So this is the thing. And once the flatten is done, we go into a dense layer of 64 neurons, and this is passed on to 10 neurons. So this is actually a multi-class classification task where I'm giving 10 neurons. So 10 classes, 10 neurons. Whichever neuron gets activated, whichever neuron gives the highest value, that is the output. So this is a sample architecture of how a CNN is constructed, what are the layers, what are the filters we decide, how the dimension is being reduced. You can see, right, we started with 32 cross 32 image, and we reduced the dimension to 4 cross 4, and then we converted that into a one dimensional structure, and then we gave it to the new artificial neurons to do the classification process. I hope you understood. I have just explained the convolution process twice. I hope that you guys would have understood. It's a beautiful concept, and just because of this concept, a lot of algorithms have been designed and evolved, and the entire computer vision today is being ruled just by this simple concept of convolution. So yeah, we had already gone through this, but still I'll give a revision. So we say we have the ground truth, or we have the labels, so we know what our the actual value is, and then we use the back propagation to train and to improvise the algorithm. So we initialize for the filter values. I said before, we randomly plug in, let's say we plug in all ones inside. So for all the filters in all the convolution layers, the values are going to be 1, and in the fully connected layer, all my weights and biases are going to be 1. So I'm going with this initialization. I plug in all the values, I give the image data, I do the convolution operation, reduce all the dimensions, and then I give it to the neural AN and parts, the dense layers, and it will try to do the activation process and come up with a classification value. So let's say the output should be 1, but the output is 0.4. So the error rate, next step, we calculate the error, that is 0.6. and using this we try to update the gradients. So now you can see it's a huge process because we have a bigger network. We not only have the fully connected layers, but we have also the convolution layer. So now you need to find the gradient value of each pixel of the filter with respect to the loss function, and then update all the internal pixel values based on the gradients that you observed. So man, this is a very big process, and that's way out of the human mind or for our calculation. That's why we go for computers. They will take care of the things. So this is how the CNN gets trained. And now we are going to come up with an important concept called as transfer learning. So this is also the one of the types that comes in learning. So what we had observed in this slide, that there are a lot of computations, then there are a lot of calculations, and training a, see, you would have observed that training a neural network itself takes a lot of time. Then man, just imagine training a CNN, how much time it would take, how much computations, how much calculations are there inside, and how much time, when the in 1990s or 2000s, I guess the neural networks, the training before the advent of GPUs or harder or advanced processors, training of CNNs would take months and months of time. If you train a CNN in CPU, it will take around months. So they to reduce this, and man, I can't just sit with a research project, train a CNN, and then wait for months just to get one output or just to get one model. Because in research you have to do different several analysis. Just for one analysis, if it takes 1 month, then to publish a paper, it will take around 2 to 3 years for me. And by the time I'll graduate from college, and I don't know what's going to happen next. So this was the scenario at back then. But don't worry, due to the advancements in technology, we have high processors, we have advanced GPUs, and this will help in conserving some time. But there is an additional thing or an additional technique or a process that helps you to conserve more time, which, my friends, we call it as transfer learning. So transfer learning, as the name suggests itself, we are trying to transfer something. We are going to take some knowledge and we are going to transfer that knowledge. So this is how the transfer learning works in a very brief or in a one-liner. So if I want to explain transfer learning, let's take two CNNs. So we call a CNN called as a pre-trained CNN or a pre-trained neural network, and we use that pre-trained neural network in our neural network to perform our task. So how this thing works is, let's say, I'll just go, I'm not going to use an example, cite an example, but we'll go with the actual thing that happens. So there are some data sets or some very large image collection data sets called as ImageNet, ILVRSC, and then we have CIFAR 10, CIFAR 1000. So these are some huge collection of images, around millions of images on different classes, 10 classes, 1000 classes, on daily objects like coffee mug, and then we have the water bottle, and then we have a cycle, a plane, a bird, a sheep. So all the different objects that you see in your common life, or common objects that you see in your life. So a large amount of images have been collected and a database has been generated, and the neural networks have been trained on this, and it definitely took a lot of time. But what they did is they stored. So what happens in the process of training, the model will try to find the optimal values for the weights and biases and the convolution filters, and once it is trained, we freeze, we lock in all the values. That's what we do, right? We say when we save the model, we lock in and we freeze all the parameters. We just keep with this, we're not going to do further training, and we use that for prediction. In transfer learning, this is where the magic happens. What I'm going to do is I'm going to take that model that is trained on one particular task and use that for my task. This might sound bizarre. That what are you saying, Sairam? That I am going to take a CNN which is trained on common image objects and I'm going to apply on my project which is going to find brain tumor from MRI. How does this going to help, man? How, why do you even do this is a question you might have, because I'm completely out of domain, right? That is trained on sheep images, on coffee mug images, and I'm going to use that model to find brain tumor in MRI images. How is this even possible? I know you have this question, but why we are doing this is to conserve time. Instead of starting from scratch, we start with something. Sorry for that. So we start with something. So what we do is we take a CNN, but there is one catch. You need to construct the same architecture as what they did, because if you change the architecture, you change, even if you change a single parameter of one neuron or for anything, then you can't transfer the weights. So this is the catch, but still there are some more things I would like to explain. What happens is, if we are constructing a CNN as same as the pre-trained CNN, then you have to directly transfer all the weights and give. But this doesn't stop here. Why should I just stop with their own CNN? It looks like copycatting. And how copycat? So I just take their own algorithm and I implement. Then how can I say that this is mine? I've just used their algorithms. I say, why do you stop with that? Design your own algorithm, add more layers to it, do your customization, but after that part. So your neural network will have a combination of the pre-trained existing neural network and some of your own. So what happens is, you have a big bucket in which you have the pre-trained network and you have your own network. This part is already trained. It has the optimal values. So you don't need to train it much. You can freeze the training. This part is where you need to do the training. So this part will just perform the task of feature extraction, dimensionality reduction, and this part, my friends, is where you are going to do train on the MRI images or on your domain images. This will conserve a lot of time, and this will help you to give a kickstart or a boost. Like, instead of starting from 0% accuracy, you will start with maybe 40, 50, 60, 70, 80. That depends. I can't guarantee that, man, use this CNN, use this pre-trained network, you'll get 80% accuracy in the first epoch. No, I can't guarantee that. But instead of starting from scratch, you start with somewhere, and this will help you conserve some time. Don't worry, I will be talking more about transfer learning, that pre-trained neural networks, in a separate session. But just understand what transfer learning is and how it helps to save time when you train CNNs. So as I mentioned, so some of the standard algorithms of the pre-trained networks we have is VGG16, ResNet, DenseNet, Inception, EfficientNet, Exception, Inception, ResNet, and then we have MobileNet, NASNet, ConvNet, AmoebaNet. There are a lot of variety of pre-trained neural networks. Like, those people took all this train, they took all the vein and pain, and they trained their neural networks from scratch for hours and hours together, and then they have given us the weight file they have given to us. They say, come on, man, you live. We have done all the things we want. Let me pass on it to you. Take the weights, enjoy. So you just take the weights, put in your network, add some more layers, and train it. The hours and hours of training, or the months of training, has just reduced to hours of training or minutes of training. That drastic time reduction is why this is what explains the power of transfer learning. It's yet a simple concept. It's a simple concept, yet a powerful one. You just drastically reduce by the training time by 80 to 90% just by using this particular concept, by using the pre-trained neural networks on your task. So that's the power of transfer learning. This is what I mentioned, the ImageNet. So it has 1,000 classes in it, has millions of images, and the pre-trained models that I've mentioned here have been trained from scratch on this data, and the weights that you obtain are used on your project using transfer learning. So I hope you would have understood about the CNN, what's the convolution operation, what's the pooling operation, how the stride works, how the padding works, how a CNN is constructed, how do you train the CNN using backpropagation, and then we saw about transfer learning. We saw about the pre-trained CNNs and how they help to reduce your training time and how to give a kickstart or a boost to your image classification or computer vision or whatever DL projects. So now we come to the last part of the session, where we are going to talk about the potential solutions to some of the challenges that we observed in DL. I'm not going to cover all challenges, I'm not going to cover all solutions, but I'm going to just talk about the few ones and the most important ones. So some of the challenges or some of the solutions that we can use it, as I said, I've just listed. This is just a very small list. There is a huge list that is there, but let's just stick with the very important ones. So we have batch normalization, we have regularization, so these, and gradient clipping. So these techniques will try to solve the issue of underfitting versus overfitting. This one, so batch normalization and regularization will help in reducing the model complexity, and it will prevent overfitting, or it will help in improving the underfitting conditions. The gradient clipping or the unsaturated activation functions can help in solving the vanishing and the exploding gradient problems. Initializations can be used in better backpropagation processes. And then online GPUs, like you have Google Collaborate, you have Kaggle, which give online GPUs. And now the world has shifted towards cloud. So AWS, Azure, Google Cloud Products, GCP, and many more cloud services provide online GPUs. You can use them. It's not necessary that you need to buy the big hardwares and just keep set up at your home and connect them with PCs and monitors and all those stuff, and then you need to do the training. That's not necessary. You can use the online GPUs. And the last part is the interesting topic called explainable AI techniques. So one issue which we have is model interpretability or model explainability. I hadn't mentioned in the previous video because now we're going to talk about that. So these are some of the solutions. As I said, I'm not going to go deep. These are just some things that because we haven't yet started with the practical side. Once we develop a CNN, and once you start developing a CNN, then you will understand what is overfitting, what is underfitting, what is. I have given great theoretical explanations, but man, none of the explanations will come close by self-realization, and the self-realization you will come when you practice or when you code CNN and do a image classification project on your own. Then you will understand better. No matter what Harvard level of explanation I give it to you, it will be better for you. But the best explanation is when you realize on your own. When you do a image classification project and you find training may you have 90% accuracy, but in testing you have 50% accuracy, then you will understand it is overfitting. Then you will try these different things, and when you practically try, you will understand, okay, when I use this technique, the overfitting is getting eliminated, and you will remember it. That is the power of self-realization, self-learning, and practical learning. We will come up with that slowly. So, but as of now, I promised it's just a master class. It's just on the fundamentals of deep learning. So now we have the regularization techniques, which I have mentioned. So we have four base regularization techniques, out of which three would have already seen in machine learning. We have the L1, L2, L1, L2, and then we have dropout. So dropout is something which you would have not known, which I'm going to talk more. So dropout is a layer that is present in a convolutional neural network, or sorry, in a neural network generally. In addition to the dense and all the basic stuff we have, there's an advanced or an additional layer called dropout layer. So this dropout layer has one parameter known as the probability value. So we give the probability and it randomly cuts off the neuronal connections. So let's say we have a first layer with 4 neurons, and that is connected to 4 neurons in the next layer. So we'll have this much amount of 4 cross 4 connections. We will have 16 connections. If I take the dropout layer with a probability of 0.5, so it will randomly connect 0.5 of the connections, means it will eliminate 8 connections. So if you remove the connections, you're reducing the parameters and you reduce the model complexity, and this will help in reducing the overfitting. Yes, I didn't mention more because that is not the topic of interest today. We just need to understand what are the different regularization techniques. And then the other three I've mentioned here, L1, L2, and L1, L2. So these are also present inside. So these will be helping in the back propagation process. So you can see the formula I've mentioned here. So initial part is just the loss function, but in addition to the loss function, we are adding a regularization or strict regularization parameter, which will result in a stricter loss function, because the loss function, the aim is to reduce the loss. That is the ideal objective for us to find the best weights, right? So if I keep a stricter loss function, or if I regularize on that loss function, then there are a lot of chances that I can get better weights, and this will help in improving the performance, and this can help in improving the overfitting or the reducing underfitting or the things. I'm not going to go deep, but just understand that these things will help to improve the performance of a neural network. It can help, it will help, or it's not, it's, I'm not saying will, it can or might help. We can't, we are not astrologers, I can't predict everything. So just some ideas that we can give which can help in improving the performance. And coming to the last part and the last slide of the presentation, explainable AI. So we are going to talk about model interpretability and model explainability. So we have a term known as black box. So students who have an electronic background will know what black box means. Don't worry, I am there for all the other students or the computing backgrounds or whomsoever. So black box is nothing but, it's, let's say we have a box or something, and we give something inside, it gives something outside. So for example, like a lucky draw. So a lucky draw, you just like let's say I have an hidden box. Inside that I have chocolates. I'm just telling you to put your hand inside and take a chocolate. So you just put your hand, you just take one out. You take Cadbury Silk, for example. Next time you do something, you get a 5 star out of it. You have no clue that what chocolate you can expect out of it. You just give something, you put your hand, you take out something. So this is called as a black box. Black box means you give an input, it gives an output, but you don't know what happens inside, what the processing is. This is, my friend, the problem that we observe in deep learning. The deep learning models, as you increase the number of layers, you go more and more, and you try to go build complex architectures, and you try to build better algorithms, and your focus is more towards the accuracy. Man, I have to increase more layers, put more neurons, put more layers. When you go more and more, the operations become more complex. You saw the convolutional neural network itself. It tries to reduce the features, it tries to reduce the dimension, extract the features, and give it to the classification. It tries to do the activation functions and all those things. ANN was quite simple to understand, but CNN is a bit advanced, right? When I add this part, but this helps in improving the performance and achieving. So as we run more and more towards accuracy, we are deviating and going away from interpretability and explainability. This is also an important objective that you need to understand. See, let's say I'm designing an AI algorithm in a healthcare sector. So let's say you are giving an MRI image and I'm trying to find brain tumor. So how does a CNN do? It says, yeah, give me the image, I'll reduce the dimensions, I'll do convolution, I'll do pooling, I'll do all those things, and I will give it to the dense layers, and this will do the activation function, and it will give an output and saying whether the patient has brain tumor or what. Doctor will be like, huh? What did you just say, bro? I didn't even understand anything. That's the problem. So when you design a research project of this and you just say, wow, I've cracked the case, man, I'm going to go pitch it to the doctor, I'm going to make a startup and I'm going to earn in millions. But when you go to the doctor and you show, and the doctor asks, how does this work? He says, very good, pa, this project is good, it is giving good results, but how does this work? And you explain that, sir, this is a convolutional neural network. You have the convolution filters that does the multiplication, addition, and the dimensionality reduction, and then the classification, the backpropagation. Doctor is like, what are you even saying, man? I'm not even able to understand any of the thing. That doctor would have years and years of experience, and he will say that, bro, look at this region, this is the result, and because of this only. So he gives a proper explanation, whereas the neural network is not able to give that explanation. This is why we call neural network as black box, and it lacks explainability. So the accuracy is not the only goal, and you should not run always behind accuracy. You should also consider the other objectives, and one of the most important objective is explainability or interpretability. This was one of the trend or one of the needs in research, and that's why a set of techniques called as explainable AI or interpretable AI techniques came into existence. And now the research paradigm has shifted into this side, and they're focusing on these objectives also. So always remember, don't run behind accuracy, go for all this. So it must be an holistic objective that you should satisfy. So you should have a good accuracy, you should have a less error rate, and you should have a robust or generalized model. It should be lightweight, it should not be too complex, and it should give explanations also. So these are some of the wholesome concepts or holistic objectives that you need to satisfy to develop a good algorithm. So this is just the basic. So once you apply the explainable AI techniques, it will give explanations. So let's say you take an image and you say that in this region I find something abnormal, and because of this I am saying it has a brain tumor. Now my friend, this gives an explanation, this gives trust or confidence. Without blindly I am saying that this has brain tumor, and in another case I say because of this I am saying it's a brain tumor. You give a reason, and this explanation gives a trust or a confidence or a belief in what the neural network says. Even still, they won't understand the internal working, but you say that, sir, you can see the image that the CNN has analyzed. It is finding that in this region there are some abnormalities, and the CNN has focused more on this region, and based on that, it is saying that this particular image has brain tumor. So this gives a kind of belief. That's where there is an interview question here. What is explainable AI? What is interpretable AI? Explainable AI are a set of techniques that try to find explanations to the predictions, whereas interpretable AI will try to find interpretations for the prediction. What, man? What are you saying? You just said explanation AI for explanation. You're saying interpretable for interpretable AI. What's the difference? Explainable AI focus more on the external explanation. Give the data, it will focus on why or what is the reason in the data that the model is trying to say that this belongs to a particular class or a particular prediction. Interpretable AI, on the other hand, will try to focus more on the internal parameter of the internal working and parameters of the model, and it will interpret that for this image or this data, this is how the model has worked, and by following this procedures, it has come up to this result. So two different ways and two different operations, but ultimately we are trying to explain or give reasons or give some additional proof, and this adds belief or it gives a trust and confidence in the explanations or the predictions made by the models. So you have different types. Some of the algorithms will do feature importance. So for example, we have a data set of the standard COVID data set. So we have cold, we have cough, we have headache, we have leg pain, and we have chest pain, and we have COVID. And any person or common person will say that leg pain is not even associated. So we give lesser importance to leg pain, whereas we give more importance to chest pain, cold, cough, and other things. So this is called feature importance. So I can say to the doctor, if I ask how this algorithm works, I will say, sir, you can just plot the feature importance and you can say this algorithm is giving major importance to cold, cough, headache, and the chest pain, but it is giving the least importance to leg pain. And by this model is trying to classify and categorize whether the patient has COVID or not. So this is an explainable AI technique, and this gives the explanation. Then we have counterfactuals, we have parameter importance, we have what the parameter interplay, like how one parameter associates with other parameter. There are a lot more things inside. I'm not going to go. Will be a separate series on explainable AI where I'll be covering in depth on the different techniques and also. But just understand that these are some techniques that we can use to provide interpretations or explanations to the predictions, and that adds trust and confidence to the predictions made by the models. So, guys, my friends, we have come to an end to this deep learning masterclass. We started with the fundamentals of deep learning. We started with what a neuron is, what a neural network is, what is backpropagation, what are the different challenges, and what are the different tasks associated. Then we came with CNN, and then we saw the convolution pooling operations, and then we saw about the transfer learning, and then we saw about the pre-trained neural networks. We gone through the ImageNet database, and then we come up finally with some solutions to the challenges, where we saw the regularization techniques, we saw the online GPUs, and then we finally come up with model explainability or model interpretability using explainable AI. So with this, we have come to a conclusion of the deep learning masterclass. I really hope you guys had enjoyed this session. You were able to appreciate and understand the concepts very well. I tried my best to explain these concepts with real life scenarios also. I hope you enjoyed and appreciated those concepts. If you really like this content, don't forget to like this, share it with your other friends who are interested to learn deep learning from the conceptual manner, who are interested to build a career in AI. Do subscribe Biomed Bros, do follow and keep a regular eye and keep a regular watch, because I'll be posting a lot of videos like this. I'll be posting master classes, I'll be posting some short videos, I'll be posting some cheat sheets, some interview questions. I have a lot of things planned in my mind, and which I'll be slowly executing as time goes. So feel just subscribe to Biomed Bros, like the content, and if you have any doubts, feel free to put it in the comment section. And I've also attached the link for the WhatsApp community. You can just join the community. Me and some of my other friends are there, who are always more than happy to help you guys. If you have stuck with any project, if you're stuck with anything, or you want to build a career, or you want some mentoring on a particular project, whatever it is, we are there for you. So we have a bunch of grateful hands who are ready to help with you, whatever problems or whatever concerns you have. We are ready to help for you. So we'll see in another masterclass. Till that, signing off. Sairam Adithya. Happy learning. Bye bye.